bad enough that I have to introduce myself. So my name is Stefan. I'm from Siemens Corporate Technologies. Since early of this year, in January, our department has the fancy name Simulation and Digital Twin. And actually, this was also a reason, or actually in the beginning before, we made some thoughts about what is a digital twin, what could it be, what will it be in the future, and this is the thoughts that Roland Rosen, Christoph, Heinrich, and myself had, and we just want to present them to you and hope for good discussion afterwards. So I'll start my talk with some collection and to get a feeling of what is a digital twin. So it's seen now at the Hanover Fair. We have seen that there are many people say, oh, there is a digital twin. So what's in there in this digital twin? So I started to collect. So obviously some kind of CAD model, all those digital representations of real twin can be in there, but as well requirements that you have in an electronic way can be there. You have something like simulations of all kinds for being it CFD simulation, being a mechanical simulation. All this stuff are there, and you probably see here they form a kind of digital structure there. But there's even more, that there's control algorithms that define how the things operate. Here you see some points, some larger dots, some smaller dots. So in the whole talk, I will want to reduce everything, all the containers of the digital twin actually into circles, dots, and lines. So if you go out and say, oh, digital twin, let's call it circle, dots, and lines. So circles stand for something like simulation models. Dots are data artifacts, and lines are connections. So we want to keep it somehow simple in this difficult thing. So okay, now you have the simple models, so you connect them together, and this is probably showing something like a new object, and this can be part of the digital twin. But think further, you want to produce something, then you have something like the planning for the production line in there. There are also simulation models in there. Also you have some more detailed simulation for the assembly. So also there, even further, some more detailed simulation about ergonomics when you include the environment as well. And also then, if you go into operation, you get some performance data there, and then the objects themselves, they deliver you some sensor data. All these together is all contained they are all digital, and let's say, okay, this could be something like a digital twin, because it is digital representation. And during the operation, you do not always use everything, but you select a part of it. So that's key message one, that you have all these things there together and you use parts of it. Never ever all the things. So going more into details, I was always asked about definition of a digital twin, or what is it. So we have in the paper, we tried to define it. Actually, I'm not sure if it helps a lot if you define something. Then you have it defined, but you want to separate from everything else. So what is in the digital, what's not in there. Actually, I think that doesn't help you a lot. So I'm trying more to describe the digital twin by its characteristics. So I think that the digital twin is the somehow semantically linked collection of the relevant digital artifacts. So it doesn't make sense to throw everything and collect everything in there. Then you end up with a, let's say, digital shoebox. You throw everything in and you hope to find everything else. So that will not be very successful in the end because just of the sheer mass of the things that you have. Then another aspect is that the simulation models that are in the digital twin, they are specific for the intended users. That's what Timo also said. You have a simulation model for something, and only because it's a simulation model of a car, it is not useful to do a crash simulation in there. They are specific, they are there, and this is something I'm going to show you, that, okay, the knowledge is there, and you can build on that. You have to modify it a little bit, and then you can also do that something like the digital twin, that it evolves during the life cycle. You get more and more knowledge in there. It integrates it in a somehow still structured way, and that why do we need something like concept of a digital twin? Actually, it's not for itself. It has to be a user. So it only makes sense if you have such a construct and if you really want to derive solutions out of it. So you must already have in the beginning somehow an idea what you want to do with all these data. So just collecting them could be an approach, but I think makes more sense to think in advance what you want to do. So let's look at the life cycle or the typical times that you approach during the life cycle in a normal development. So during concept design, you start with a concept. Obviously, you have some requirements. You have already there, if you do it the clever way, you define a system architecture, you define what you are going to do, then you go more into the product engineering. There you have this domain-specific simulation models, you develop them, you design them for an optimal product, you use them, but actually you forget normally or often a lot about what you have done before. You have the system model there, but there you do something different in there. Then it goes even further. If you go to the commissioning phase, you collect a lot of data, you optimize your product, you use it, you have here a lot of data that they are there, you verify your requirements, but okay, so you have probably some simulation models to help you, but it's also a separate stage. And then in the end, in the product, in the operation, you ship your product, it works well, then probably after some times you get some customers that, oh, it doesn't work anymore, and you start to think about, oh, what could be wrong, or is there something, so you use your field data, you start to actually re-engineer your product again to find out what is there. And I think that this is situation that as it is right now in many companies, so even Siemens, as we say, we are very digital, they are still working in that way. So wouldn't it be better to use or to plan the future use of all these digital artifacts in advance? So one aspect which I was discussing yesterday is as well, so is actually you have to close the cycle there. So you normally don't start from the green field. You have already experience, so you have an idea what from earlier products what could be interesting for the further use. So now start with concept design there. You close the feedback loop. You see already what could be interesting in the later phases. You define the goals there. What a digital twin or parts of a digital twin can be usage, and you define a general overall structure how these artifacts that evolve during the life cycle can be there. Then in the next, during the engineering, you get a lot of CAE data you have. There you are able to define actually the general structure of your digital twin. You have it there. You see here, oh, actually I like, I have also squares in there, but these squares are only placeholders for the real elements because they are at these phases not yet available, but you know that they will become there in the later phases. So you walk further, you replace some of the placeholders, with the models as they go there, and then also the data are available, and in the end you end up doing the operation with the whole structure filled in, the data are available, and the very big benefit is there that you don't have to re-engineer your product again. You already did it with a little more effort during the engineering phase. So I think that that's a new way how, or a new approach how to think there. So in the beginning you all speak about having the role of a system architect. Probably you need something like a digital twin architect that keeps already in mind in the early phases what's the future use of all these things. This is also some aspect that I just want to go there very shortly. Also, if this digital twin artifacts are somehow modular in there, you can also use it beyond the product itself. You have also your production system, you have a modular, you have the exchange. So Timo showed already that there are standards to exchange parts of your digital universe with others, without IP problems, without all things. So in general, that's available, and you just have to have it and to really live it, and then it can be that you exchange parts from the component to the product, to the production system. There is in the design, but also there in the production system operation. This is the part of where we move from the normal world to more and more the cyber world, where the product communicates with its production machine or further on. So there are several value chains aspects that there are as well for the digital twin. So you can use it in the development, you can use it in the operation. It's in the end it forms a kind of comprehensive network for all your information there. Okay, so enough theory. I want to show you one example where we did all this learning curve in there and applied it. So it's a very simple object. It's a point operating machine. Actually, the point operating machine is this is the drive that shows in the net when train network operates the train plates from left to right. It's actually a very simple system. There's a motor in there, you have some mechanical drive that puts the rotation into horizontal movement there. This point machine S700K is sold for many years. As soon as I work for it, I see them everywhere in the train networks all over the group. But as I said before, these tracks are very relevant, and these operating point machines are very critical for the functioning of the infrastructure. So in the last time, there was only actually just scheduled maintenance. Somebody goes there, and if it doesn't work, okay, the trains have to stop, and somebody has to check manually. So what started to say, okay, wouldn't it be good to have some detection system in there? But in a railway, it's very remote, so it's difficult to put sensors out there. But one sensor you have, that's the current or the power consumption of the motor. So you can measure them centrally and look at them and look at those curves. And if you see some derivations, then you say, oh, probably there is something wrong, and you have to go there. But this failure detection is only one thing, so we want to put something more into it. So we want to also simulate it, the failures, and then, therefore, by combination of this detection and simulation, you can already identify what is wrong, so that the serviceman can go there, or even better, can go there in time before the failure is so relevant, and therefore increase the availability of the network. So, as I said, this machine is actually not so easy because it has this driving aspect, but also on the track there are some components in there, and these are very different from situation to situation. So there are some mechanical locking systems there. The track is sometimes old, sometimes new, so we have to combine the machine model with an environment model and have everything. So what we have done there was re-engineering the system. So great. Was re-engineering, we built an AMSIM model, a mechanical model of the point machine. We also put the same for an environment, introduced some failures, and so we were able for these S700K to reproduce failures and compare them with real measurements and go there. So that's the idea. So how we did it actually in that first slide, the old way. But as time was, now the ELS 710 is on the market for half a year, and I said, okay, now we have learned something. We knew that these engineering models are already there from the engineering. And we want to give an additional benefit to the customer, say, okay, your maintenance is critical, and we want to supply something very nice, very modern, have some VR application where you can have already a training and you can already simulate all these failures, and in the end probably also combine real data with the thing. So we said, okay, lesson learned. We have all those things. We start already during design of the new point machine with thinking about the end. So we designed those application as well. We used the simulator with an environment model, put them all into a VR environment, and this is something I'm going to show you in the end. It's just a video that is filmed up from a Microsoft HoloLens. So you see, actually, this is what my colleague is seeing in the glasses. So there's the application, down there is the track, it's operating, and you see the simulated data in there. You see here the electric power as long as in synchron with the movement of the tracks. And see, now it moves back. And you can also, in the first view, you have seen the movement there. You can here show the electric power. And so now we are simulating a scenario that somebody is blocking or something is blocking down there in the. So you see the curves are there. Already there that identifies, okay, there must be something in the track because of the signature of the electric system or of the movement system, and it also has some solutions in there. What could be the reason for that? So it's more than enough to help you. And you see there, it's really a live system. So somebody came in there and it's just protected there. Here we have a slightly different, actually you see a slightly different failure that's more common than the blocking. That is now you see that it's not blocking, but it's going badly. So that there are different reasons for having this increased power consumption there. It could be the locking device or the sliding place or the installation conditions. So the people that do the maintenance, they get these suggestions what they should look up. So I think that's really all, and I have to finish in time. Where's the last slide? So I want you to have this takeaway message to take them home, that this kind of next generation digital twin contains all the relevant digital artifacts in a defined way. It allows the reuse of information with little extra effort for realizing new services. It uses executable simulation models for the prediction of system functionality, and it combines pre-planned and well-coordinated artifacts and semantically used connected data. The digital twin will evolve along the life cycle and finally it becomes part of the realized system. So that's it, and I want to, if there's any question right now, otherwise I'll put that in the discussion afterwards.
Thank you for your presentation. So how do you relate then the augmented reality to the real world scenarios? Like, are you trying to correlate any of the actual failures in the field towards, like, is there a learning model also behind it? Or I'm not sure what I'm seeing.
Actually, two ways. So what we've realized there is just a demonstrator what we want to do, but we want to superimpose it onto the real track.
Right.
So by recognition, I say, okay, that there it is. And we are right now working on some algorithms to classify the deviations from the original, or from the should be to the real behavior, to identify, or to identify is probably a far goal, but to narrow the possible root causes of the errors. So some of those errors are pretty easy to detect because you can coordinate it somehow with the moving parts. So if the parts are not moving, then they probably don't work there. But sometimes there is more complicated because there are several reasons possible. So we're also thinking about AI, but there it's very, very difficult to have realistic data, and so we have a lot of measurements there, but we don't have data. So data is more than measurements. It has also to be the information, what was the reason for a misfunction, and to use something like artificial you need a lot of defined situations where the system can learn. So right now we follow more the approach from the physical side, that we simulate some dedicated failures and create some patterns, and then we classify the measured curves with these predefined error patterns.
Yeah, because in the Netherlands, where they discovered that temperature was a big issue in these switches. So they now place sensors, you probably know about it, so they can heat up to a certain extent so that the failure is going to be dropping, but still it's a very interesting problem.
Yeah, there are even the colleagues from the mobility department, they told me it's so difficult if you have some train switches close to a chemical industry. So even if the air is clean, it's not clean. It depends on what they are producing there. You can see it in the performance there. So sometimes, and weather is always. We all know that in the winter you have snow, you have things. So
that's why I liked your first, like one in the first minute of your talk. You said the remote areas, and then I said, you have a lot in Europe.
In your talk, you mentioned that you introduce the failures already at some parts of the simulation. So I'm wondering, were you able, with this forward technique, I would call it, to generate all failures which appear in reality?
No.
And have you thought of other techniques that looking at the topological interaction of the components to come up with a technique which is able actually to reason about the construction?
All failures are actually not possible because actually they do not know which are often because they hardly do any analysis what went wrong. So it doesn't work. Then usually the guy goes there, puts some grease on it, visit it, and then it's okay. And there are hardly any protocol and everything. But we know some main failures there, and these we reproduce, and then hopefully we cover about 70–80% of the failures in the field, and with all the others, we didn't care right now about that.
Because for a relatively simple system, it is understandable. But imagine if you take a Siemens turbine, then
I think this, so we are quite happy with this system that it is so easy. But if there are situations when you have 6 or 7 point machines acting on one blade, then it gets more and more complicated. So but for the simple one, this forward